Okay, so my plan for today's lecture is to go over one very small example of a certified program. So the idea is to show you, give you an idea of how what is involved in doing such a project. Okay, so the task that I'm doing is very toyish, but it should kind of illustrate some of the kind of ideas that or difficulties one might face. So the idea is very simple. You have a simple expression language, okay, and so that is our source language, and we want to compile it to a stack machine. And the stack machine, as you know, has a stack, and there's a push operation and apply operation, which applies a operation on the top of the stack. Okay, so this is essentially the problem. So I will ignore the other aspects like parsing the string to get an expression and things like that, and I will just directly work with the heart of the compiler, which is translating from the expression captured as an abstract syntax to a program for stack. Okay, so the way we model this is you first, so you might have a some language, so you have you capture the. I hope my screen is visible, right?
Yeah, yeah.
Okay, so capture the abstract syntax of the language, source language. So again, so the abstract syntax is the syntax of the language stripped out of any useless things like bracketing and things like that. So in our case, our expression language, you can capture the abstract syntax like this. Okay? So expression is either a constant. So your expression is either a constant, or it is, let's say, expression. Or its expression, some operator expression. Okay, so it's a pretty simple language. So this operator can be either plus or minus. We can have more operators, but yeah, for illustration purposes, we'll just keep two operators. Okay, and
so
this is
when you write your expression, it will be like.
So, for example, if you have an expression like 2 plus 3,
it will be written as constant 2,
constant 2
plus constant 3.
So for example, this particular example would be
apply
compute of
apply constant 2 plus constant 3.
bin operator. So this is
plus constant 3. Okay.
In some sense, this is how. Just a minute, hold on. Just a minute, hold on. Is the screen visible? No, right?
No, no.
Okay, now it should be visible, right?
Yeah.
So, so this is how you represent 2 plus 3 cells. And the point here is that in the abstract syntax, we don't talk about bracketing and things like that because those are not relevant for the semantics of the language. So it's all those superfluous things like the bracketing, the operator precedence and all you can ignore because this is after you have parsed the language. This is how you represent it inside the compiler. Kind of one can forget about about things like bracketing and operators. These things you can kind of forget when you are in the service. Okay. So this is our source language. Okay. And the target machine is a stack machine, and the stack machine has two instructions. Either it is a push of a natural number, or you execute a binary operator. Okay. So the stack machine has a stack, and there are two possible. There are two possible instructions, and let me just give this a name. Yeah, so the stack machine has a stack and two possible instructions, and a program is just a list of instructions. Okay, so you execute the instruction one at a time, and if you encounter the instruction push, you will push that value onto the stack. And if you encounter the instruction exec with a binary operator, what you do is you pull out the two elements on the stack and apply the operator and put it back. If the stack doesn't have enough elements, there is an error. That's your semantics of the machine. Okay? And what we want is a compiler from the expression language to the stack machine. Okay, so this is the problem that we want to look at, and we want to look at it as a certified programming kind of task, and we want to prove the correctness of the compiler which we are going to write. Any questions here?
No.
So let's move on. And so the compiler, again, we can kind of write it quite easily. So you have an expression. If the expression is const of n, the instruction that you generate is push of n. And if it is apply of op e1, e2, then you first compile e2, then compile e1, and then you put exec op on top of the stack. So remember that this will be the topmost element on the stack. Then comes this elements, and then comes this element. Okay, so this is a compiled program. So we can try compiling some code. Okay. Call 3. What did I call it? 2 plus 3. You'll see some instruction like push 3, etc. Okay. So this is your compile. Now what we want to do is we want to show that this compile is correct. Any questions?
When you do 2 plus 3, the instructions will be push 2, now push 3, followed by push 2, followed by the list will be what? Push 3, push 2, and exec plus.
Yeah. So when the stack machine runs, it will first push 3, and then it will push 2, and then it will have exec plus. So it will just pull out 2 and 3, add it, and put it back. Okay. So this is the compilation thing. Okay. In real compilers, what we have is we might have some optimization phase, and there might be some optimization rules, and we probably want to show that certain optimization rules are correct. So you say something about how this optimization transforms the code and this. But here we are just interested in plain simple showing that the compiler is correct. Okay. Okay, so now if we want to talk about compiler correctness, we have to talk about the meaning of the program. Okay, we have to give a meaning of the program. We have to give what it means for the machine to execute a code. These two things we have to have, and if you have that, we should be able to kind of connect the source program's meaning to that of the target program's execution. Okay, so we have to talk about the semantics of the of the languages that we have. Now, the point is that we can do it abstractly, or we can, since we are working with Coq and we are trying to prove things in Coq, the way we capture the semantics is by giving its meaning as a Coq value. Okay? Some kind of a denotational meaning is what we give. So we give meaning to these programs in terms of Coq expressions. Okay. So let's look at the meanings that we want to give. Okay, so first let's give a meaning to the operators. Okay, so take any binary operator. I want to give it a meaning in terms of function from NAT to NAT, NAT to NAT to NAT. It takes two NATs and produces a NAT. Okay, so the meaning that I assign to plus is the natural number addition, and the meaning that I assign to minus is the natural number subtraction. Okay, this is the meaning that I associate with the operator. Okay. Okay. Now, for the expression, what is the meaning? Okay, if the expression is a constant, so it takes an expression and produces the meaning of it. So here, let me put it this way: the meaning of a binary operator is a function that takes two maps and produces, and it is defined as follows. And the meaning of expression is the meaning of the expression is in it. And we have given the meaning. So constant n, the meaning of it is just n. If you have apply of E1, E2, then you apply the meaning of the operator on the meanings of the expression E1 and E2. That's it. Okay, so pretty simple semantics that we have done. Okay. Now we have, so by this means we have given a complete meaning of what our source language looks like. Okay. Often this itself is quite challenging. If you have a source language which is like C or some such thing, it is quite complicated. Okay. In fact, COMCERT, which is the certified compiler for C, which is written in Coq, they have a model for C language that they have to formalize this way. Okay? They should have a model for through which you can precisely capture the meaning of the C code, so that we can show that the compiler is correct. If you want to show that the compiler is correct, what we need to show is that the compiler preserves the meaning. Okay, so the meaning of the program, source program, and the meaning of the assembly generated should be the same in some sense. That is what your compiler is supposed to do. I mean, characters of the compiler.
So, but if you want to do something like this,
so let's compile these things. Okay.
Yeah, I have a question. So, it is easy to do this because Galena is functional. We can do for only functional things, no? For C.
No, so COMCERT is a C compiler written in Coq.
Yeah, but how do you do that? Like if you have a C.
Oh, you have to for C program, you will have to capture some logic where you can talk about pointers and things like that. So there is the separation logic which is typically used for such things. So there will be a formulation of separation logic inside Coq.
Okay.
And they use that to do it.
But they won't be carrying precise values. They will be only talking about same point.
No. So in some sense, the point here is that you can think of this. You can think of this expression denote as a kind of interpreter for your expressions, right? So interpreter written in Coq. It might not be efficient, but it's an interpreter. So in some sense, what you want is an interpreter of C language written in Coq. You don't care about the efficiency of this language because you are going to use it only for proving things. Okay, so you don't really care about the efficiency of the interpreter, but you definitely need such an interpreter. You need a denote to work with it. Okay, the more complicated the language is, the more complicated the mechanism would be. Like if you, for example, if I want to change this expression language and I have variables in it, I cannot do expression denote by just taking an expression, but I also have to take an environment which maps variables to values. and then only I can talk about the meaning. So it changes what expression denote would be. So similarly, things will have to change. So if you have a C language, then there is a heap associated with it. So you will have to have some way to capture the heap, and those kind of things will come up.
Okay.
Okay, but you definitely need to capture the meaning in this case. Okay. Now look at the stack machine. We have to also capture the kind of meaning of the stack programs, stack machine programs, right? So how did we do that? We define stack to be just a list of natural numbers. That is the internal state of your machine, and each instruction does something to the stack. Okay? It takes a stack and produces not necessarily a stack, but option of stack. The option is a data type which returns an optional value. So option of A is either none or it is some A. So if you should think of this as some way of expressing an erroneous value of A.
This is just and nothing.
Just and nothing in Haskell, and option in OCaml. So it is either sum of A or it is none. Okay? So for example, let's try this out. So you have an instruction. Let's say push 5. Let's say we have a stack which is just empty list. Then you'll get some. So the result is a stack with 5 on it, but we are indicating that there has been no error. But if you try to do something like exec plus, then it will say none. So that you have hit a error condition. So let's put just one value there. Even then there will be an error. But if you have 2 values, then the exec will give you a stack where 2 and 4 are popped. They are added and put that. Okay. Okay. So that is what an instruction is supposed to do to the state of the machine. The machine state is captured by the stack. Okay. So in some sense, for the stack machine is just the stack, and instruction is a state. Together. Okay. So this is what the instruction does. And what does the program do? It just executes one instruction at a time. Okay. So program denote P with stack st is it will give you back an option stack. So what does it do? If the program looks like some instruction followed by some program pp, then it will first execute the first instruction. If there is no error, then it will execute the next instruction, next set of instructions. If there is an error, immediately it will bail out. Okay, and if it's an empty stack, then you don't have to do any transition. You just give this. Okay. Okay, so we can check this out. Dropping. That will be inserted 8. Now that we have captured the meaning of the expressions, we have captured the meaning of the stack machine programs. We want to prove that the compiler that we wrote is correct. Okay. So how can we do that? So essentially, what we are trying to prove is something like this. To start with a program, start with any expression for every expression. Okay. For every source program, if I compile it and then I run the machine on empty stack with that compiled code, what it should give on top of the stack is the value of that expression. Okay, so this is the correctness criteria that we. Does this make sense?
Yes.
For every expression, if I compile it and get a program, and if I execute it, that should result in the stack having the value of that expression on the top. This is what shows that the compiler is correct. Let's try to prove this.
But we don't know if E compiles.
Sorry?
Okay, so all expressions are valid, yeah?
Yeah, for all expressions.
No, I mean like when we say a well-typed expression is always valid, it will always compile.
No, in this case, the expressions are just our simple expressions. Right?
Yeah, but it, yeah, so
no,
but yeah, but well-typed means it's correct. It will compile.
Yeah, but here the expressions we are talking about is the expressions of our expression language, which are, they don't have any types. They are just natural number types. There's only one type. It's a unit.
No. I mean like when you write like apply, plus, constant 3, constant 2, and so on. If you write any well-typed expression belonging to EXP, then that's a valid. It will compile and it will also run.
Yeah.
And that's why you are able to write some of this thing, because you are not writing nothing or.
It is not none.
It is not none. But
not only is it not none, it is also the case that the expression is the value on the top of the stack is the value of the expression.
Yeah. But in general, not all well-typed expressions may be compiling. Yeah.
What do you mean by in general?
Like for instance, you can write a program in Haskell which will compile, but it will compile, but it
yeah. I mean, I'm talking about this compiler.
Yeah.
This case, okay. There are other issues when you look at much more complicated compilers, but this is a toy example. So this is our compiler correctness criteria. Yeah. Okay, so let's try proving this claim, and we'll soon see that this is not easy to prove. This is not possible to prove. So we start by introducing E, then we do an introduction. The first case is just sum of n is sum of n. It's a trivial thing. But the second inductive case, we have to prove that program denote of compile E2, compile E1 plus XX on empty state is on empty stack is some denote of this. Yeah. But our induction hypothesis is not in a good shape, because what happens is that we will have to kind of somehow show this. See, when you run this program, right, on the left hand side, you see my mouse, right? So when you run this program, think what is going to happen. We'll first run the first expression, okay, and on empty state, okay. But now you have a non-empty stack, and on which you are going to you are going to run the expression E1. So merely having this induction hypothesis on empty stack will not help us prove the claim. So we have to kind of abort at this point. There is no way to proceed further with this. Okay, so we need something more general, and that is what we want to do. Okay, we want to prove a slightly general version of this program. It will require some experimentation to figure out what exact generality you need, but we will this particular example will work out. But I just want to kind of show you some variants of it which will not work out very easily. Okay.
But if you just take any stack, if you just allow it to be any stack, and if you just say program did not compile of E, and let's say there is a list access, and then you just say it's some expression is not E : access, will it work?
Yeah, so that is roughly the thing. You can see it on the screen now.
Okay, okay. Yeah, yeah,
Look
yeah,
at the
yeah,
form.
yeah, yeah, yeah.
So the point is you have to generalize this. See, because first thing that we realize is that on empty stack is not enough. So we have to generalize on for every stack. Okay. So the first version that you might come up with is something like this. Um, um, the first version you might come up with is like saying for all E in expression and for all SP. Stack prog denote this is something you might want to do. Something like that is what you might come up. Even this is a problematic thing because so let's look at this case. You have a situation where you are not talking about probe denote of compile of something on some stack. You have a compile of something and some extra program sitting here. Okay, so it is so you will have to generalize on the continuation of this expression also. Okay, the rest of the program also you have to generalize over, and that is so that is the reason why you the general form that you have is for all expressions, for all stack, for all continuation, for all programs that comes after the thing. Program denote of compile of E plus plus P on SP is the same as run the program P with the expression denote on the top of it. Okay, so this is the version uh, of um, of correctness that you want. Here, what to get the original proof, what you are going to do is you are just going to replace SP with empty stack and P with the empty program. Okay, and do some rewriting to and that's essentially it. So you can kind of clearly see from this compiler is better, you can get to compiler is correct with some rewriting. Okay, that I will not do, maybe it's left as exercise. It is not it is straightforward but not trivial per se, because you'll have to substitute and do some rewriting to get it. Okay, so let's go over this proof and let's look at some salient features of it, and then I think we are kind of mostly done. Any questions here? So this is often, I mean, this is like the anti-Polya advice. So Polya had this advice that if there is a problem that you cannot solve, then find a simpler version of the problem that you can solve, right? And try to solve it. But this is kind of the anti-Polya kind of dual of that, or the
stronger claim. You are trying to prove a stronger.
You may make a stronger claim and try to prove that, because the stronger claim will be more applicable. Okay, so that's it's the anti-Polya method of doing things. So instead of proving a special case, you prove a general case. Any question? Okay, so let's go over this proof and let's look at some interesting peaks for this code. Okay. So I spent some time writing this proof, maybe about 10-15 minutes to complete this proof, to get the right sequence of tactics to do it. But don't concentrate on the tactics and get lost in the tactics, but just look at the overall picture, and we will kind of discuss this tactics, how did I figure this tactic out and all those things. So let's start with the theorem statement. Okay, so let's see. So I have a for all E, for all SP, for all P. Okay. So the first version I did was an intros. So initially I did an intros. Okay. So then I will introduce all E, SP, and P. Okay. But the problem with this is that if I do an induction on E, I'm going to do an induction on E anyway. Okay. But if I do an induction on E, I won't have the for all SP and for all P coming in. Okay. It will be for a particular SP and for a particular P, and that will not work for me. So I need to be careful about how I introduce it. So I introduce only the expression P.
Yeah. So do you know like this Fitch diagram for natural deduction? Like
What diagram?
Fitch diagram. I think it is called Fitch diagram.
I
Like
do not know this.
yeah. So for natural deduction, you have this thing called Fitch diagram. Like basically you want to prove that E implies something for all E. Yeah. So you introduce E and then you prove something. You get P, and then at the end you discharge the claim, and then you will get E arrow P. Yeah. So yeah, so in Fitch diagram, what you do is that you will write E, and then you will write a line wherever E extends. And so if you so that so it just clicked me that when you say intro E, that is you are assuming E. Yeah.
Yeah, I am assuming. Yes, correct.
All right.
But the point here is that there are many variants of this statement. For example, I could have changed the order in which I do and I do this proof, right? These are same. But if you try proving this part, then if you have to get to E, because essentially you are going to do an induction on E. There is induction on ST and induction on P does not make much sense.
Yeah, because you don't know the structure. Yeah.
Yeah, I mean, because they are not interesting. The compile is on E, right? So you have to do induction on E. And if you put it this way, the problem is that to reach E, you will have to introduce ST and P. Okay. So imagine that. So this is like in mathematics, you say that for all cows, some property is true. Then you, if you want to prove something like that, you say, let me pick an arbitrary cow, and then I'll go ahead proving it, right? So in that sense, what is going to happen here is that we are going to pick an arbitrary stack, arbitrary program, and an arbitrary expression, and then go about doing it. But by this time, when you do an induction on E, the ST and P are fixed. Okay, and remember why we came to this point is because we wanted to choose ST and P appropriately. Okay, so this method won't work, so we have to put E here. Okay, you will realize this only after writing one or two variants of this code. Okay, it's not easy to come up with which is the kind of order in which you need the variable and how much you need to introduce. Okay, so I introduce E. So now you see the goal that I have is for all stack, for all program, prog denote of compile E of P, ST is prog denote of P, expression denote E, ST. Okay, and then I do an induction on E. So notice that now the inductive claims are all quantified over the ST and P. That is precisely what I want. If I do it in the other order, that will not happen and I'll be in trouble. Okay. Okay, so now I need to tell you something about this dot and semicolon. What is the difference? If I do a dot, what happens is that tactic is applied and maybe potentially many goals are created. When I do a colon, what happens is that this tactic, so induction E, if I did a dot here, that means that induction E a tactic is applied and two goals are created. You can see this, two goals here. Okay, and then one of them is focused. Okay, and on that focus thing, I am going to apply simple. Okay, whereas if I give semicolon, what it does is that for each of the, so as you give semicolons, the first tactic is applied. On each of them, the second tactic is applied, etc. Okay. So now what is happening here is that this is, I have simplified both the goals that is generated. The two goals remain though. Okay, but it's in a simpler form.
Simplify means just substitute.
Simplify is essentially carry out beta reduction. Essentially, not fully, because you have to be careful. Substituting definitions and all are sometimes not okay. Okay? There is a compute which is problematic, because if you do a compute here, then sometimes it might be really bad. Compute will just blow up things, and then you will have a crazy looking expression which you don't want to deal with. Okay? So,
but a beta reduction is essentially substitution, no?
Yeah, it's substitution, but it will not do full beta reduction, is what I understand.
Okay.
So you should not do compute. If you do compute, often what happens is that the structure is completely gone. Sometimes compute makes sense, but sometimes it doesn't. But mostly simple is what you want. Okay. Okay. So the induction hypothesis, the base case is trivial, so we dispose it off. Now we come to the induction hypothesis. So let's move on to the induction hypothesis. Now I have what? I have to prove for all stack, for all P, something happens. At this point, I can introduce my stack. Notice here that the induction hypothesis is in terms of ST and P. So I have a for all ST and for all P here, which is very convenient. If I didn't have that, I will not be able to carry out this proof. Okay. Oops, what happened? Okay. Yeah. So I introduce ST. Okay. Now I have to do a program denote of compile E1 plus plus compile E2 compile E3. So just remember that the plus plus is write associative. So when I have plus plus is a list list appendix. Okay.
Yeah.
So you have A plus plus B plus plus C. You should read it as A plus plus B plus plus C. Okay. This is what you should read it as. Okay. And what happens is that what we want is we want to clearly get compile E2 plus plus something as our object here. So we apply the append associativity in the. So let me just show that. So how do I figure this out? See, currently what the goal looks like, the current goal it looks like probe denote of some expression, okay, plus plus P. Okay, this is the form in which I am currently.
Yeah.
Okay, but this something is not compile of something. Okay, it is some complicated thing. And I want to get it, if I have to use the induction hypothesis, I need it to be compile of something E, right? So I need to rewrite it using the associativity of
plus plus.
So how do I figure out what lemma to use? So there is you can search for it. What we are going to do is we are going to do a search. So I'm going to do a search. I roughly want and understand what I need to do. Equal to something. Okay. Lemmas of this kind is what I'm looking for. If I search, I immediately find app ASOC, which says for all LMN, L plus plus M plus plus N equal to L plus plus N plus plus N. And this is precisely what I want. Okay. I want to rewrite the right hand side as the left hand side. Okay. Okay, so I have to do rewrite in the opposite direction, and that is this arrow is being shown. If I don't want to do rewrite app ASOC, that will replace L plus plus M plus plus N to L plus plus N plus plus N, which is not what I want. I want the other way. Okay, so I want to do it in the reverse order, so I do it. We will see what happens if we do the reverse order. So now you can see it becomes compile E2 plus plus compile E1 plus this thing plus P, and that is in good form, right? Because it is like in compile E2 plus some program, plus some program. So I can apply the inductive hypothesis for E2 on this, and I will end up with getting this is same as probe denote of P denote this.
Okay. One second.
Yeah, so let's go over it.
Okay.
So after this, notice that this is like probe denote of compile of E2 plus some program ST. Okay, and I know that probe denote of compile of E2 plus some program. Remember, this is quantified over all P. So that is why I can use it. Okay, our ST is equal to probe denote of P expression denote of E2 ST. Right. So this portion is what I'm going to replace. Okay. So this is of the same form as this. You can see that?
Yeah.
Okay. So I'm going to rewrite with IEH2. So the left hand side will become probe denote of the rest of it. That is compile E1 plus EXEP plus T ST. That is what I'm going to get. So I'm going to rewrite. Now I apply again and I rewrite with IH1. Now I am in good shape. I just do a simplification and then it's a trivial goal and I dispose it.
Okay.
So that is essentially the proof. The proof essentially follows from the associativity of the app operator.
QED just disposes of the introduction. Huh? What does QED does?
No, QED just says I am done. I am done with the proof.
Okay.
So the point is that if I try to do a QED here,
Mhm.
the clock will say that you are not allowed to do it.
But where do you dispose of the intro which you did?
That is done here. So intro, then I'm doing an induction, right? The induction base case is trivial, and this is the second
Once
bullet
it is
is
done, it is automatically.
Yeah, it is gone.
Okay.
Okay, so this is the proof of the correctness. Okay, I've gone over the tactics. I've kind of told you how we figure out what is the kind of lemma that we need to use, and in this case, it seems to be AppSOP. And I searched it by doing a rough match of what is it that I want. Okay, so it will search in the types of the lemma that I have and gives you those things, and you can try to apply this. I will now go over this and see what happens if there is a bug in the compiler, and we'll look at in detail of how to make this code better, this proof script better. Any questions here? Okay, so to summarize, what a compiler like this will have a source program and a target program, and what we need to prove correctness is you need to have a meaning for the source program, you need to have a meaning for the target program, or you need to have a model for the machine, target machine where you are compiling to, and then you have to show that the meaning is preserved under the compilation process. This is the essence of all compiler kind of situation. Okay. Now I want to kind of deliberately introduce a bug in the compiler and see what will go wrong. Okay. Recall that in the compile code, in fact, when I first wrote this code, I made this bug. So I had written compile E1 and E2. These are not the same if your operators are not commutative, right? So the point here is that if you read the stack after this, read the program. So you will first execute E1. The value of E1 will be on the stack. Then you will execute E2. Then the value of E2 will be on the stack. So E1 is bottom. E2 is on top. And then you are applying the operator. So it will be E2 of E1, not E1 of 2. Okay. So this is a bug in the compiler. Let's see where it goes. Let's see how all this will just work out. There is no. Okay, so now we come to the proof part. We do an introduction. We do all these things trivial. Everything goes.
Okay. But by the way, in that previous proof, where did we use the meaning of plus?
Oh, we used it at the
except B, yeah.
The except B was defined in terms of the operator binom, so that is why we use the meaning of it. But the point here is that you'll see where the bug will be seen. Okay. So I will apply AppSOP first, and you will notice that here IHE2 is not what we want. IHE1 is what we want because of the order in which things happen. Then I will apply this thing. Then I need to do IHE2. So far, so good. But after simplification, you'll see what is going on. You will see that probe denote P, binom denote B, okay? Expression denote E2, expression denote E1. The binom denote P, this thing, is equal to binom denote in the other order. You see? So you know that you have got the order of the expressions wrong. Okay, and that you realize when you find that this is not trivial to prove. Okay. Okay. So so at this point, what you need to prove is bin denote B, expression denote E2, E1 is same as bin denote of in the other order. So then you have flipped the order of the expressions in some order. So this bug you can catch when you do the proof. Okay. The point is that you could write test cases for this, but I mean this is as good a test case as I can think of because it clearly tells you where you have done a proof. Okay. So let's go back and fix it, and then be done with.
So if it was only plus, we could have used
Yeah,
rule for
yeah,
plus and got
yeah,
it again. Yeah.
yeah. What went wrong? Okay, so the proof is done again. That's one thing. The second thing that I want to say is that this proof is not really nice. Okay, because we have too many steps, and we have not really captured the essence of the proof. Okay, so what exactly is the essence of the proof? The essence of the proof is, so let me give you some improvement on this. Okay, so I essentially apply the associativity of the append operator. That is really what I have. Right? So I can rewrite this a bit more. I do this as much as possible. So repeat. So I'll just remove all these things. I do a repeat. Okay. Then I can rewrite both these things. Okay. This is a much better proof because it kind of clearly tells me that essentially what happens is I just rewrite it. Rewrite with app.
So when you say repeat rewrite of opposite,
So
it
it
does
will
for
apply.
both the hypotheses.
No,
What does
no.
it
What
do?
it does, so when you do repeat, what it does is it, repeat of a tactic will run the tactic as many times as it is successful.
So if you have a, so what you're saying is that if I have an expression E1 plus plus E2 plus plus E3 plus plus E4.
No, no. It is not nothing specific to this example. Repeat of a tactic will apply the tactic as long as it is successful. So you can think of this as run the tactic once. If it is able to kind of simplify the goal, then run it again till you cannot do it anymore. Okay, it's a danger. Repeat rewrite is a dangerous tactic. I'll tell you that. Why? Because if you rewrite with associative, with commutativity, for example, it will always succeed. It will always succeed, right? You will rewrite x plus y as y plus x plus y as y plus and keep on going. Be careful about repeat rewrite. Okay. So repeat rewrite. This is a dangerous thing. But in this case, it is okay because you are making progress. Okay. Okay, so there is another thing that is problematic here. Okay, the other thing that is problematic here is, see, I am not using these variables st and p anywhere here, right? So I can just do an intro. I don't have to have variable names for it. So that is better. That is definitely better than this. Okay, I could do an intro here and then do an induction E. This is bad practice because I really do not know this E. Is it the same as this E? So I have to. It's better to keep an name explicitly there. But this one is fine. Okay. The other possibility I can do is I can do it trivial because simple trivial is always there. So I can just get rid of the base case. So, this is also there. Yeah, so much I have done. But there is one serious problem here, which is this IHE1 and IHE2. Okay. What is wrong with it? Because these are names that I didn't produce. It was produced by Corp. Okay. And there is no way, maybe next version of it might call it small I HE1 and small I HE2. So I have no way to kind of really figure out what is going on here. So this is not really a very robust proof script. Okay. So I probably need to improve on that as well. Okay. So how do I improve on that? So let's see what happens when we are in this situation. Okay. So there are a couple of ways in which we can improve this. What we want to say here is that I want to use this inductive hypothesis here. Okay. So I can do one thing. When I do an induction, I can give explicit variable names. let me try giving variable names here. Is it no? So my names are not good because so there is EP is a bind operator, so that is off. Let me call it. Then E1. Two. Now I am in good shape. So that is E1. IHE1 is expression. No, I don't want that.
But what is this? I don't understand. Induction as.
So the point is there are two cases for the induction. The base case, I don't give any variable name, but if you look at the hypothesis that I have, I want to give them suitable name, because if I don't give them name, the names are picked by COP. Okay, so this IHE1 and IHE2 doesn't make sense. Okay, because the next version of COP maybe it will change the names. So you don't want to do that. So you will kind of want to figure out what exactly are the names.
What is this square bracket mid?
Yeah.
What is that? What is the meaning of that?
That square bracket tells what are the names that I need to give for these hypotheses.
Okay. And what is this bar?
There are two cases, right? There is a base case and there is the induction set. So, I mean, in the base case also I can give some variables here, but yeah, that's not relevant. So because it is handled by simple trivial, I don't need the variable name, so I can ignore that. In the induction case, I need the names, but these names are not nice. Op is called bin op, E1 is called E1, and E2 is what I want, but I have got IHE1. So the order in which I need it is different. Okay, now I am in good shape. So I see op is a bin op, E1, E2 are expression. IHE1 is my my induction hypothesis on E1. IHE2 is my induction hypothesis on E2, and then I have this. This is a better proof script. Okay. Okay. So this is definitely a better proof script, and I can probably make it even better by kind of automating it completely. So that is what I'm going to do. So what I'm going to do here, essentially what I want to do is I have to apply the inductive hypothesis. Okay? Is it okay if I let me check whether it is okay if I reorder the rewrite? Will that also work? Is what I want to know. It doesn't work. I need it in this order. Okay. So this is important. So what I'm going to do is I'm going to change this code a bit. Okay, and you will see what is going to happen here. I am going to do the following. I am going to write a tactic here, which will pick the. So I don't want to give these names. These names are not nice. I mean, I have to figure this out. Okay, so I can do it like this. Match. This is what I'm writing is a tactic. Okay, so what this is not a Galena script. This is a tactic. So what I'm going to say is that suppose I have an inductive hypothesis which looks like for all ST, P, okay. If this is my, I have this as a hypothesis, rewrite it with it. Rewrite everything. So the goal is here. These are the hypotheses. This is the term style. So if I have a assumption of this kind, try rewriting with it is what I'm going to say. And just repeat. And if I don't have this, I do a so let me see. my input shape. Uh, mm, so this doesn't seem to work. Oh, on two things. So, oh, it has done it once. So, yeah. So, okay. So what did I do here? I was just saying that, okay, see if you have an hypothesis which looks like for all something, probably not of something equal to probably not of something. If you have one of those hypotheses and whatever be your goal, just rewrite it with IH. Okay. And if you're not successful here, you do a simple and trivial. Okay. And repeat this many times. And you see that this is going to dispose of all the proof. Okay.
What
So
do you mean by,
I can do it this way, and I can just ignore all these induction hypothesis names that I give.
so what
Now
does what does the turnstile do?
So the term style is, so I want to match the goal. So what I'm saying is that look at the current goal.
Okay.
If the current goal looks like, this underscore means match anything. But I have a precondition which looks like IH of, which looks like this. So rewrite it with this. Okay. So so when you look at the goal, at any point of the time, you have a goal, right?
Yeah.
And the goal is like you have to prove this under these hypotheses.
Yeah.
Okay. So what I'm saying here is that match the goal. I don't care what the actual goal is, but if your hypothesis has something of this kind, for all something, prove denote of something equal to prove denote of something. If you have such a hypothesis, just rewrite with it. I don't care what it is.
Okay. Okay.
Okay.
And
now notice that
what is this? What does rewrite do? You don't tell it how to rewrite.
Rewrite means you figure out what these variables have to be. You unify it with the goals. Okay. So what you are trying to do is your goal looks like something equal to something, right?
Yeah.
And let's say if you are rewriting with IHE1, that also looks like something equal to something. Okay. So you try to unify this something equal to something with this, and that will give you some variables, some matching for ST and P and all those things that you instantiate IH1 with those things and rewrite.
So it will be you basically using your premises. No, what is?
Yeah, it will be using, in this case, it will be using my premise. Okay. See, rewrite is a very simple idea. I'll tell you what rewrite is. Let's see what app ASOC does.
Okay.
App ASOC is the lemma for all A. L, M, N list of A. L plus M plus N equal to L plus M plus N.
Yeah.
Now when I want to rewrite it, I have to pick particular values of A, L, and M, right? In my current situation.
Yeah.
Okay. If you look at my current situation, I have a goal.
But what if your goal was like A plus plus B plus plus C in bracket plus plus B plus plus E plus plus F? Yeah. So you have two applications possible.
So it has to. It will try to figure out one of them. It will not work out in that case. You have to be careful about it. Okay. It will figure out one of them. So what it tries to do is, you have an equation here, right? Some subterm is here. It will try to match one of the subterm and rewrite it.
Okay.
Okay. There is a rule for it. Knowing that rule is not very important, because if you know the rule and if you are going to use that rule, that is a bad proof script. Okay.
Is it like
Because
in
you have,
Haskell, like the outermost expression or something like that?
yeah,
No,
it
it's
might be
not this.
outermost expression or something like that, but it is not good to kind of rely on that behavior. You
Okay.
see,
Okay.
because you definitely don't want your proof script to be that flaky.
Okay.
Okay, if something changes, it should not just break.
Mhm.
Okay, so that is why
So you
you
are
want
saying that it should be deterministic when we
the co-op system might be doing something, and
uh-huh.
you can figure out exactly what it does and try
Okay.
to code your tactic to make use of that. But that is not good idea, because
Yeah.
maybe something changes later on and then you don't want to break it.
Yeah. Yeah.
Okay. Okay. So now the point here is that if you look at this yeah, it's on, right?
All right. All right. Thank you.
Yeah. Yeah. So I also throw in a simple and trivial,
Mhm.
because things that can be handled trivially, I think this will probably, this is not required. Even the other case efficiency. So let's see. Okay. So let's try this. And at this point, I do an induction on E. So it doesn't. No? What happened? Did it finish? No. It did I miss out on anything? Mm-hmm. It didn't work out. Oh, I need an intros. I also need an intros, so I will do that. The stack and the thing, so I need to do that also, right? I need to introduce the stack thing. So here I say that if it looks like some list of nat to something, then I do intros. Or I can just say if it looks like something arrow something, I just do an intro.
Yeah. So one thing, good thing is that if you do this way, then you can write one thing for binary operator, tertiary operator, and so on. Yeah.
Yes, exactly. That is the point.
Yeah.
Yeah, so I want to make this robust enough that it works no matter what. Don't care what is here. Yeah, so let's see. Yeah. Now I think I can do also crush here. So I have kind of completely automated this script. Okay. And this is the final form in which I want the proof, because if you notice here, I am not doing anything specific. Okay, the only intuition I have is whenever there is an append there, I need to apply associativity enough times. Okay, and most of the time I am just doing a trivial, simple kind of thing. And the only point where there is some kind of domain specific language is that whenever I have an inductive hypothesis which is applicable, please rewrite with that. That's all. Okay.
Yeah.
You don't want to make this crush very specific to this proof. Okay. Because tomorrow, if you change, as you said, if I introduce a tertiary operator, okay, then this should work still.
Yeah.
Okay. So I don't want to be too specific here, but if I can automate some of these things, then the final code will be much better. Okay. So I think I'll stop here. I think I have given you a flavor of how proofs of this kind work. And I also wanted to give you a kind of hands-on way of looking at these things. So there are a lot of interesting topics we have not covered, and I don't think it is possible to cover it. So yeah, I think I am done. And I mean, rest of the time we can maybe chat about what other things can be done and what are the interesting kind of things. And you can, it's mostly driven by questions.
Yeah. So, yeah, I have some questions. So the thing is, so
shall I stop sharing? And
yeah. So this proof is without failure. Yeah, that means it always works. So there is no compilation error.
Yeah.
But in general,
there is
no,
so this example I have taken from the certified programming book, so you can check this. There is a typed version of it. Okay, so which is a little more complicated because the stacks now will have a type system and all those things. So it is not so easy to deal with those things. But there are variants of this you can have a look at. Yeah. So that's the point. So the errors, handling errors is another.
Like your program might compile, but it might fail.
Yeah.
So in that case, we will have to modify our assertion.
Your semantics has to change. Your semantics
has to change. So in that case, you will have to write something like if it runs, then it is some, otherwise it is none. Yeah.
Partial correction.
Yeah.
Kind of.
And
but the problem with that assertion is that you can have a trivial compiler which always emits a failure code, right?
Yeah.
That will satisfy this property, so it is not very interesting in that sense. But yeah.
And also there are higher abstractions because maybe it's a monad. Yeah. This some none is also a monad. So
yeah,
the standard way you handle this thing is with a monad. Yeah.
Yeah.
So such kind of things that techniques are also there in Cork.
Yeah. I mean, you can kind of capture monads and all those structures inside Cork as well, because you can do that. There is, I mean, it is not a there is no IO monad in that sense, but all the other monads you can capture.
So there is no print function in Galena.
There is no. I mean, Galena is a purely functional programming language. It has to, because otherwise there is the type system you cannot use to prove things.
Yeah.
But what you can do is instead what you can do is that whatever you can do the technique which is to encode the effects. So if your program has some effects, you capture it as a data type. Okay, and you can use these ideas of effect monads and things like that to kind of say what they do. Because if your program can do only few kinds of things, that you can capture, right? You can capture
but it can't print like you. There is no IO monad like you said.
There
There
is
is
no
no main
embedded.
function. There is no main
There's no
function.
main function. There's no system. Yeah.
Okay. Yeah, it was a wonderful intro. I mean, I don't know, maybe because I had some exposure to Pascal, so I could actually, I mean, syntax was not a big problem for me.
Yeah.
I just started to figure out, yeah, I'll try reading up that software foundations book.
Yeah. So any other questions or comments? So we have looked at only the programming aspect of it, the certified programming aspect of it. The mathematical proofs part is slightly different. If you're looking at some library like MathCom, they have a completely different way of doing things. And there the concerns are different, whereas here the concerns are slightly different. So yeah, there are two kind of styles in some sense. If you want to deploy Coq to prove a math theorems, you might want to use MathComp way of doing things because they already have formulated things like vector spaces, fields, complex numbers, those kind of things, and they are adding a what do you call it? This analysis library also. So MathComp is the way to go if you want to do math proofs. Currently, that looks like the way to go. But if you want to do the the program correctness kind of thing, you will have to stick to the standard library. There are other libraries like STDPP, and maybe they will give you a richer kind of feel. And there is also a STD Lib 2 that is in progress.
And
One problem with the ecosystem is that if you are using the Coq system, because it's so powerful, you can have your own versions of libraries, right? You can use your own standard library. So that so initially that is a problem because there will not be one standard library. Some different projects will use different, and then you will kind of try to stick to one of those libraries. There is no blessed library in that sense. And as I said, depending on the kind of view that you have towards programming, towards proofs, I think you might want to go towards the math comp kind of way of things. So those are the kind of things that.
And what is the main difference between Coq and Agda?
Agda is more like a so what Agda is mostly the way I see it is that it is more towards the programming side of it. Okay, so they didn't have a tactic library, for example. Okay, so the way it used to work is that they have inline refining of programs. Okay, so you can think of it as they have only the refined tactic. Okay, but the type system also of Agda is slightly different. Okay, and Agda allows some more richer kind of types, and there are so if you are more approaching this problem from a programming perspective, not as a proof, you are not really interested in the proof, but you want to do the correct by construction kind of proofs that we did in the last lecture. Maybe Agda might also be a nice option to do. The other mechanism, the Coq has a very powerful notation mechanism. So you can another kind of strategy that you can do when building programming language kind of thing is to write EDSs, embedded domain specific languages, inside Coq. So you capture the language as an AST inside Coq. Don't write a parser or any such thing. You prove things about the ASTs inside Coq, just like what you did here, and then what you do is you kind of give notations which are convenient, so you can use it inside Coq. So you write the program inside Coq. Okay, so that is another way to solve the language problem. I mean, you don't have to write a new compiler and all those things. You just use it as a embedded language inside Coq. Yeah. One of our projects is for writing low-level crypto code in Coq. You write it in Coq and export it to C. And that C code is what you execute. But the point is that there will be no array out of bound problems there, because wherever you have used an array indexing, you have to give a proof that it is within the bound. And those proofs might be complicated, but we have tactics to automatically dispose it off. So the user, it will feel like you are writing code in C or maybe even low level. but the code will be correct in the sense that never will there be an indexing of the array beyond its bound, and there'll be no mismatch of Indianness and these kind of. So there is one such project that I am involved with.
Okay. All right. Thanks a lot. Thanks a lot.
Okay. Okay. Thanks for the opportunity. See you. Hopefully, we will have it
So maybe
sometime in
Shankar
person.
can conclude.
Yeah, thank you, Piyush, for the course. I'm
Thanks.
sure it will be useful for many people, especially since it's on YouTube, so we can look back at it later on as well.
Okay. Then see you. Thanks for inviting me for this talk. We'll hopefully meet sometime in person and have more interesting, more interesting sessions, I guess.
All right. Thanks a lot. Bye.
Okay. Bye.
Bye.
Bye.